Okay, welcome back. This section is about balance, basically. In a nutshell, that's what it's all about. So 7.6. We want to talk about moments, centers of mass, and then centroids. Okay. We'll start in one dimension and then go up to two dimensions. That's what it is. So first off, what is mass? And mass is the measure of a body's resistance to motion. Okay. So you've seen the mass element come up in this formula, F equals ma. If you're an engineer, you beat that formula to death. But right here, M stands for mass. Okay? So this isn't hopefully something that's too out of the ordinary for most people. But anyways, let's start with one-dimensional problems. And first, what is a moment? So a moment, in particular about some origin, is the tendency of a system to rotate about a particular point. Okay? Tendency of a system to rotate about a point, in this case the origin. And the formula for the moment is always going to be the sum of the masses of the particular objects times their distances from the origin. Okay, so it's going to be the sum of m sub 1, x sub 1 plus m sub 2 times x sub 2 plus dot 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 all the way up to m sub n times x sub n. Okay, so a fine example, problem 1 from the book. They tell us some, you can do it like a table, but m sub I and then x sub I, and they give us a bunch of masses. So the first mass is 7, and its location is -5. The second mass is 3, and its location is on the origin. The third mass is 5, and its location is 3 units away from the origin. So you could literally draw it like a number line, and here's our fulcrum. So it's kind of a teeter-totter scenario. We have one object sitting there. Its mass is 3. So I'll label it that way. And then 1, 2, 3, 4, 5. We have this guy over here. Its mass is 7. And then 1, 2, 3. We'll just put 3. And then this guy's mass is 5. Okay. We want to know its moment about the origin. And you can kind of speculate, okay, it's going to be tilting in this direction. This guy won't really affect the moment at all. It'll just end up in the sum, it's going to be 3 times 0, right? So the moment about the origin will be 7 times -5 plus 3 times 0 plus 5 times 3. Right? So we'll get -35 plus 0 plus 15. In other words, the moment about the origin in this case is -20. Okay. Of particular interest to us will be the balance situation, which is called equilibrium. Okay. So equilibrium happens when the moment about the origin is 0. Okay, so equilibrium happens when the moment about the origin is equal to 0. Okay. And you could kind of think of it as I need to take maybe this system and shift it over by how much to put it into equilibrium. And you can even play it that way. You could say, okay, I need to find this point, which they'll eventually call x bar, which will be the center of mass. I need to find this point such that the sum resulting from this business where we're going mass times distance. So the sum, in this case, it was 7 times -5, and then we're going to do some sort of shift of the system by x bar, where x bar will be our center of mass or our point of equilibrium. So it'd be that plus 3 times 0 minus x bar plus 5 times 3 minus x bar. And for this thing to be in equilibrium, we need m sub 0 to equal 0. Okay. Okay, so we can solve for x bar, and so how is that going to work? That's going to be, let's think about this. Distribute the 7, so -35 minus 7 x bar, and of course we want the equilibrium. We need m sub 0, the moment about the origin, to be 0, plus 3 times 0 minus 3x bar, and then plus 15 minus 5x bar. So what do we have? -35 plus 15 is that -20. So move that to the other side, and that number actually sounds familiar, right? That was just the moment about the origin of the original system. Okay, so that's important when we're trying to find a formula for x bar eventually. So anyways, I got the -20 over there. Combine like terms, so -7, -3 is -10, and then a -5, -15, I believe. X bar, assuming I didn't make any stupid mistakes, which I often do. But there's that. Divide both sides by 15, and we have 20 over 15, which is 4/3. Okay. So the deal is that we hope if we pushed our fulcrum over to the point 4/3, or over by 4/3, I guess. So we would be pushing this over by 4/3, I suspect. Then this thing would be in perfect balance. Right? Let's just make sure, right? So we could figure this out by, well, I mean, it's obvious. It has to work. If I plug this in for x bar up here via our algebra, we should get 0 plopping out. So I think we're good. The only problem maybe is to find a nicer formula for the equilibrium. So just note here, x bar is our center of mass, or our point of equilibrium. X bar. Okay, so I need a formula for x bar is what I'm after. Okay. All right. So what is that formula? How did the mechanics work? Can we make them abstract? So I noted one thing. This m sub 0 thing was kind of there, and then this other thing, -15, is that seems like it's the sum of the mass. Okay. So I think it's probably going to be something like that. Anyways, let's kind of look at it in general in order to figure out a formula here. What did I do up here? Well, this was the sum of the mass of the particular points times the position of the particular objects minus this equilibrium value, which is kind of to be determined, right? And we would want this thing to equal 0 for the moment to be 0. Okay, so if I rearrange this a bit by distributing the m sub I, and then noting I can take a finite sum and split it, I'll have m sub I times x sub I minus the sum of m sub I times x bar equals 0. Okay, so the summation is going from I equals 1 to n. I equals 1 to n, which n represents the number of objects on your teeter-totter. Okay, so This thing right here is just your moment of the original system about the origin. It's just m sub 0. This thing right here, let me rewrite it a bit. So I have m sub 0 minus, I can factor out the equilibrium point. So I'd have x bar times the sum of the mass of the individual objects on your teeter-totter, right? So this would equal 0, and this will allow me to solve for x bar then. So if I move this over there, I get x bar times the sum of the individual masses is equal to the moment about the origin, which tells me the equilibrium, the point of equilibrium will be just the moment about the origin divided by the total mass of the system. And that turns out to be our formula for the center of mass. So obviously the book will be interested in these kind of problems. So let's just take a look at one. This is number 3, find the center of mass. So again, we could put it as a table here. The first object has mass, well, I guess all the objects have mass 1, okay, and its location is at 7. The second object, mass 1 again, and the location is 8. Mass 1, location 12. Mass 1, location 15. Mass 1, location 18. Okay. So to figure out the equilibrium point, it's simply just find the moment about the origin. So you just multiply all of these and add them together. And then divide by the total mass, which in this case looks like it's 5. Plug that in your calculator, and it looks like you're getting 12 for your equilibrium point. Okay, so now once you get the handle of the one-dimensional systems, you want to amp it up a little bit and consider two-dimensional systems. And we begin with just some points in the plane. So in order to deal with this one, we're going to need 2 moments, a moment about the x-axis and a moment about the y-axis. Okay, so in order to deal with this, we consider 2 moments this time. We have the moment about the x-axis and the moment about the y-axis. Okay. And for the moment about the y-axis, it's the sum of the distances away from the y-axis. So you think of the y-axis, like my finger here, and then the teeter-totter is on the y-axis. Okay, so the moment about the y-axis really corresponds to distances away from the y-axis, which are x distances. Okay, so it's a little confusing, but it'll be m sub I, x sub I. And then for your moments about the x-axis, you think of the x-axis here now as the fulcrum of your teeter-totter. And your teeter-totter is going in this direction, in this kind of rotation. And the distances you're worried about then will be distances away from the x-axis, which will be given by y-coordinates. So this will be m sub I times y sub I. Okay, so let's look at number 9. And we're given a table of values, m sub I, the mass of the particular objects in the plane here, and then their locations, x sub I, comma, y sub i's. So the mass is 5, 1, 3. And then our points 2, 2. And then negative 3, 1. And then 1, negative 4. Okay. So I'm going to draw 2 pictures, one for the moment about the x-axis, which will be y values. So in this case, I'm thinking about the teeter-totter going like this. Okay, so, oh, sorry, hit my cat. The cat's on my lap. So the moment about the x-axis, I'm really worried about distances. Sorry, the moment about the the moment about the x-axis, I'm worried about y distances. Okay, so let me plot these points. So 2, 2. So for this first guy, it'll be 5 times its distance away from the x-axis. Okay, so it would be 1, 2. And then for the next guy, -3, 1, 2, 3, and then 1. So plus 1 times its distance from the x-axis, which is 1. And then plus this last guy, so it's at 1, -4. And its distance from the y-axis is -4. Okay, so 3 times -4. So its moment about the x-axis is going to be, if you multiply that out, -1. Okay, and then I'll worry about the moment about the y-axis. So I'll be worried about distances that are given by the x-coordinates. Okay, so m sub y then, in this case, I have, well, let's look at the points again, 2, 2, 1, 2, 1, 2. So its distance from the y-axis given by this x value is 2. Okay, so I have 5 times 2 plus -3, 1, -1, 2, 3, 1. So its distance from the y-axis is -3, so 1 times -3. And then finally 1, -4. Its distance from the y-axis is also, well, it's 1. The last guy was -3. I'm getting the two numbers confused. But the mass is 3. Its distance from the y-axis is +1. Okay, so it's these distances now I'm worried about for the moment about the y-axis. So at the end of the day, this value will be 10. For the equilibrium point in 2 dimensions, we'll have sort of 2 coordinates, x bar and then y bar. And x bar will be the moment about the y-axis divided by the total mass, which I'll just write m. And then the y bar will be the moment about the x-axis divided by m. Okay, so at the end of the day then, x bar comma y bar in this problem, it's moment about the y, 10 divided by the total mass, which is 9, so 10/9. And then on the other hand, for y bar, it'll be -1 divided by 9. Okay. All right, so from this point then, we want to consider solid kind of like, I don't know, pieces of paper. We're going to call them in the book laminar plates. So you can imagine, I don't know, drawing out some shape like this, cutting it out of this piece of paper, and then looking for its balance point. You know, so you'd be taking this thing, maybe the balance point is right there, and then you could take like a pencil or something like that and balance the object on the tip of the pencil, right? Okay, so we'll need then integrals to pull this off. So in particular then, this section 4, I'm looking for the center of mass. Okay. And I may have some region that I worry about that I can sort of carve out using functions. Okay, so maybe this guy is f of x, and then make g of x a little easier to deal with. It's just a straight line of some sort. G of x here. Okay. So I need to know the balance point of this weirdly shaped region. I think maybe it's probably right here if I tried to balance it on my pen. Okay. So I'm going from A to B. And the way you could do that is kind of section it up into a bunch of little rectangles and worry about the balance points of all those little rectangles. Okay? And in general, if you have a rectangle, its balance point, you know that is just right in the middle of it. Okay, okay, so they're going to give you a density per unit area. Usually it's per unit volume, but for these problems it's per unit area. So density is going to be mass per unit area. Okay. and they're going to give you a density constant. Okay, so in particular then, for mass, it's going to be the density constant times area. And their density constant they're going to give as the letter rho. Okay, so to figure out the center of mass, of course, we need to figure out x bar, y bar. In other words, we need to figure out m sub y all over the total mass, comma m sub x all over the total mass. Okay. So first, the low-hanging fruit is this total mass thing, right? So to figure out the mass of this region, I need to take the density element and multiply it by the area of this region. To find the area of the region, we just do an integral. Okay, so the area of this region is going to be the integral from a to b of f of x minus g of x dx. Okay. And then to get the mass, the total mass then, it's just rho times the area. So rho times the area will give us the mass. Okay, so one thing down, two to go, right? I need m sub y and m sub x. The moment about the y-axis, so pretend my finger now is kind of the fulcrum, and the moment is going to be with regards to x distances, okay? So for m sub x, or sorry, m sub y, it's always going to be a matter of summing up a bunch of masses times distances from the y-axis. Okay, so for our particular rectangles, the distances from the x-axis for any rectangle will just be given by x sub I, right? And the width is change in x. So in order to figure out m sub y, I just need to sum up the mass at this particular point times the distance from the y-axis. And the mass then is always given by rho times the area at that particular point. And so we need the area of this particular rectangle. Okay, so the area a sub I of that particular rectangle is just going to be this distance, the height, times the base. The base is just change in x. The height is f of x minus g of x. So the area is f of x sub I minus g of x sub I, then times change in x. And then we would need to multiply that by our density. Okay. So for m sub x, or sorry, m sub y, we are adding up all of these little area increments. Okay, so these f of x sub i's minus g of x sub i's times change in x's, and then multiplying it by the density. Okay, so in particular, then the mass is going to be this stuff here. So it's density times area. But then we also need the distance, so this x part of the formula here. So we need to also multiply n by x sub I. Okay. We then rewrite it so it's more of a Riemann sum, and then take the limit of the thing to get our integral. So we'll have the limit of all this jazz, and rewriting it, it's rho times x times f of x sub I minus g of x sub I times our change in x. And taking the limit will give us the formula for this particular guy, rho times the integral from a to b of x times f of x minus g of x times dx. Okay. Okay, the moment about the x-axis then, so for the moment about the x-axis, it's always a matter of summing up masses times y distances. Okay. So in this particular case, the y distance, and we're thinking of our x-axis as kind of a fulcrum, and then we're rotating about that. So we need these y distances from here to here. In order to get the distance from here to here, the center of this thing, I need to kind of do a midpoint formula. So I take f of x plus g of x and divide it by 2, and that'll give me the distance from here to here, which will be the y value I'm after for my moment formula over here. So m sub x then in that case we'll want the mass again, which is rho times the area, f of x sub I minus g of x sub I times change in x. So that's my mass, my m sub I. But then I also, so up here this was m sub I. But I also need then to multiply it by the correct variable. In this case, it was x sub I. Now I need the y sub I. And what I'm saying is, instead of using some y, because, and then we wouldn't know how to integrate it, we're going to use the midpoint formula to get this height from here to here. Okay? So the midpoint formula then was f of x sub I plus g of x sub I all over 2. Okay, so this is basically then our y sub I formula. Okay, and then of course we're taking limits as the number of these rectangles goes to infinity. The book doesn't do this, but you can FOIL out these two binomials and it looks a little nicer. You end up with the limit of the sum of rho all over 2 times, after you FOIL, f of x sub I squared minus g of x sub I squared times our change in x, which I'm kind of smushing in there. And then finally, your formula du jour for the moment about the x-axis, rho over 2 times the integral of f of x squared minus g of x squared dx from a to b. Okay. And that's the deal. Those are our two formulas, and the rest is just a matter of plugging and chugging. Okay, okay, so let's dive in there then and attack this problem and its roots. So here's number 17. I have y is x squared, and then y is x cubed as my curves. I want to find the balance point of this region that's enclosed by these curves. So anyways, y equals x squared is a parabola. It's like this. Y equals x cubed, then does that go lower, right? So if I had 1/2, it'd be 1/8 versus 1/4. So yeah, it's lower, and then it goes up like that. Let me redraw that, jeez. Okay, so y equals x squared is kind of like this, and then x cubed will go below and then above, okay? So the region we're looking for balance point of is that wedgy region right there. So x cubed is there, and then x squared is here. But in this region, x squared is on top, and then x cubed is on the bottom. So that's important for figuring out the mass and all that jazz. So let's go at it. First off, I'm going to go after the total mass. They're presuming that the density constant is rho, and that will be the idea always in this section. Later on, you may have variable density once you get to Calc 3, but we don't worry about that here. Okay, so the mass is just rho times the integral of the difference between these functions, x squared minus x cubed, dx, and we're going from 0 to this intersection point, which I think is 1. Okay, so that would give us the total mass. Okay, so this will be rho times x cubed over 3 minus x to the 4th over 4, evaluate from 0 to 1. Let's factor out 12th. So row over 12 times 4x cubed minus 3x to the 4th will be just row over 12. Let's go after now our moments about the x and y axes. So the moment about the y axis, you're multiplying by x. So it's just this junk multiplied by x. So x times that dx, and then again from 0 to 1. So I'll have rho times the integral of x cubed minus x to the 4th dx. Integrate that character, so it's rho times x to the 4th over 4 minus x to the 5th over 5 from 0 to 1. What will that be? Well, if you factor out 1/20th, you'll just have 5x to the 4th minus 4x to the 5th, so it's just rho over 20. Last but not least, then, the moment about the x-axis. So the formula there was rho over 2, and then integral this thing squared minus that thing squared. So x to the 4th minus x to the 6th dx. Go ahead and integrate that. So rho over 2 times x to the 5th over 5 minus x to the 7th over 7 from 0 to 1. And then this guy is rho over 2 times, I'm going to factor out 1/35. That'll leave me with 7x to the 5th minus 5x to the 7th, in other words, 2. So times 2. So it ended up with rho over 35. After my quick integration, because I've done these problems like 100 times. All right, so at the end of the day, then, you want your center of balance. And so x bar comma y bar, that'll equal the moment about the y-axis, rho over 20 divided by the area, or sorry, the volume. So rho over 20 times the reciprocal of the mass, which was 12 over, which is going to be 12 over rho then. And then the moment about the x-axis is rho over 35, again divided by the mass. So multiplying by the reciprocal, that'll give you, the density constants all cancel out. So we have our position is 12 over 20, so dividing top and bottom, it's 6 over 10, 3 over 5, and then 12 all over 35 for our center of mass. All right, that'll do it for now. Thanks for watching.